Hello, everybody. Welcome to this week's Zoom Wednesday edition. And we will start by looking at what we looked at last week. And we will go over here to do so. Let me make sure, the usual. I think we're okay. We have reactions of organolithiums and Grignard reagents with epoxides. But before we get into that, let's recall how we make organolithium reagents and Grignard reagents. If we start with this alcohol right here and treat it first with phosphorus tribromide, then we get this isobutyl bromide, which we can then react with lithium in hexane as a solvent and make our organolithium species here. And that will behave pretty much like it is this anion here, which we have pictured here. Similarly, we can make this type of anion down here by starting with an alcohol again, and this time maybe using SOCl2 and pyridine, acceptable short form PYR, and that gives us an alkyl chloride, which we can then react with magnesium in a ether solvent such as diethyl ether to make this Grignard reagent here, which will behave much the same as if it was just this anion right here. And we see that pictured down here. So let's look at another thing that organolithium and Grignard reagents can do, and that is they can act like a nucleophile reacting with an epoxide. Remember, epoxides are made from alkenes. If I react this with a per acid such as meta-chloro-per-benzoic acid, which you can read about at the end of chapter 11, you get a mixture of two enantiomers, 50%, 50%. And meta-chlorobenzoic acid, if you're curious. The side product is not that important here. Chloro, meta to a normal carboxylic acid, not a per acid. And you get the two epoxides, which is more important. And looks like we're using this one in the synthesis up here. This is a different one down here, but made much the same way from a different alkene. The alkene would have been here. And what's going on with the organolithium or Grignard here when it encounters this epoxide? The answer to that question is simply we attack the least hindered carbon and we get this oxide ion here, which we will then protonate using a second step. Remember, you cannot have HCl in the presence of an organolithium. You must first react your organolithium and then treat the product with HCl to get your required alcohol. So yes, we have another synthetic tool. A little reminder, the new bond we have here is this bond right here. And in the other molecules reaction, we have this new bond here. So as a synthetic target, we look at that and we think, without looking at the previous parts of this, that we had a nucleophile doing an attack. I don't have the right bond highlighted in that first one, do I? How do I fix that? I did not make this bond. I made this bond. It's going to be a lot of erasing. We'll see if we can get around it. There. And we're going with our new bonds being, yes, I had this one correct. And no, I did not have this one correct. And we're thinking about using this nucleophile and reacting it with a species that will be an electrophile on this position here, yet have the oxygen 1 carbon away. That would be a vicinal oxygen. So unlike attacking an aldehyde or a ketone where the new bond is to the carbon that has the oxygen, using an epoxide, the new bond is to a carbon adjacent to the alcohol carbon. That is your big hint for when you use an epoxide. If you need the new bond, new carbon-carbon bond, that is, on a carbon 1 away from the alcohol carbon, you want to attack an epoxide, and there's our epoxide. Similar analysis would hold down here. Why did we attack this carbon here? Simple answer. That carbon, it has 1 bond to C, 2 bonds to C. The carbon next door has 1 bond to C, 2 bonds to C, 3 bonds to C. It's more hindered. We don't attack that one, we attack this one. And our new bond is here. So if this was our target, we could think about 2 approaches. We could use a nucleophile with this piece attacking a carbonyl, which is fine. Or we can use a nucleophile that has this piece and attack an epoxide. And it all depends on what you have available. If you have this available, and then you would use this approach with the epoxide. And that is how we use epoxides with organolithium and Grignard reagents. Moving on. We have a new type of organometallic reagent. Remember, chapter 15 is about organometallic compounds. That is, compounds with bonds from carbon to a metal. And in this segment here, I noticed before the lecture started, we don't have a small typo there. We have a small typo right here, right there. And we'll talk about that typo when we get there. New edition of a book, there's always going to be typos. All right, so we've seen these first 2 reactions even on the previous page. React alcohol with phosphorus tribromide, and you can get an alkyl bromide. And you can make an organolithium, such as isobutyl lithium. And you could use that for things like opening epoxides or attacking aldehydes and ketones, or as a strong base. That's the 3 things we saw with organolithiums and Grignard reagents. You could also react it instead with this copper 1 iodide. Looking back to your first course in chemistry, copper 1 just means copper with a +1 charge, And iodide is an I- ion, so this is copper 1, which is in the old school words, cuprous iodide. We don't hardly use those words anymore. We prefer the more systematic number system. So copper +1 here is going to react with 2 moles of isobutyl lithium. So if you're into stoichiometry, you're going to take 2 of those, which came from 2 of these, which came from 2 of these. Oh, you want to get strict about stoichiometry? One of these reacts with 3 of those to make 3 of these. Oh, I don't even want to think about that. I think 3 halves. I have myself to blame. I brought up stoichiometry. And we're going to make 2 moles of this react to make 1 mole of what's called a Gilman reagent, where you see 2 of these carbon groups attached to copper. We call those ligands. There's an isobutyl ligand here. That's Ligand. And we also have another one over here. If you're worried about redox, there was no redox here. Copper is still +1. Let's do the math. Each carbon is more electronegative than copper. So each carbon's really an anion. That's 2 minuses. And if copper's +1, we've canceled one of the minuses. Copper's not. Copper has a formal charge as well. So 2 pluses and a minus. Oh, sorry, 2 minuses and a. I forgot whose perspective I was talking about. From copper's perspective, it's +1. Lithium brings another plus. That's +2. The 2 carbons are anions. It all adds up to 0. It's all good. Copper did not become oxidized or reduced. Still copper +1. So we think of Gilman's as looking like this: 2 R groups attached to a copper in an anion, and lithium can be treated like it normally is, crossed off as a spectator. And this will behave somewhat like a carbon that has a slightly minus charge. Notice I didn't yet give carbon a full minus charge like an organolithium or a Grignard. And there's a good reason for this, because copper as a metal has a relatively high electronegativity. It's not a very ionic bond. Copper's electronegativity is in the realm of 2. So these are what we call softer carbon anions. And there we have it. And we have Gilman. Gilmans do different things than organolithiums and Grignards. Similarly, we can use the approach. I won't go into the stoichiometry. We could use thionyl chloride and pyridine and make allyl chloride, then treat that with magnesium and diethyl ether to make a Grignard. And the Grignard can be reacted with the same copper. And you're going to get this anion-cation combination. And what we have here, I think we have another typo. Noticing things as we go here. This is lithium iodide. Another typo. Once again, these are side products. I'm not too concerned that you even come up with these on a test. So cation, anion here, and cation is really MgCl with iodide as an anion. We have our Gilman here with 2 allyl groups attached. The reason this is a typo is this is not really bromine, it's chlorine. There's no bromine in this line at all. But the important thing to know, this is really isobutyls attached to copper. So the species looks like this. There we go. And I've crossed off the magnesium chloride spectator. It's just a complex ion spectator. So this seems like a pretty good spot to stop. It's a short little introductory segment. We've just reviewed how to make organolithiums and Grignards. On the previous page, we saw that organolithiums and Grignards can open epoxides. Last day, we saw organolithiums and Grignards reacting with aldehydes and ketones. We're going to see that Gilmans don't do what organolithiums and Grignards do. They share some reactions, but mostly they don't share reactions with those at all. So when we pick up, we're going to look at this next page here and see all the things that Gilmans do with epoxides, with organic halides, alkyl halides, and we're going to have a preview of what they can do with these special species here called alpha beta unsaturated aldehydes or ketones. So that's where we're going to stop, and I will see you on the other side and see you 5 minutes.